Welcome, ladies and gentlemen. Welcome to the Hydrogen Forum, Technical Forum of Hydrogen and Fuel Cell Europe. The next speaker is from the Fraunhofer ISE, Institute for Solar Energy System. And the title will be Scientifically Sound Fuel Cell Characterization. I asked him what sound means. Sound means scientifically based. It's no hi-fi or something. It's scientifically strong in a way. And I'd like to invite Ulf Groos to the stage, Head of Department Fuel Cell Systems.
Thank you very much. So welcome everybody. I'm happy to have this talk here, and if you like to know more afterwards, please visit our booth. We are over there, C39. So who we are and why we are there. Let's give you some facts about my department, which I'm heading. So as you have already heard, we are from the Fraunhofer Institute for Solar Energy Systems. We are situated in Freiburg, which is in the very, very south of Germany, near the Swiss border, between Swiss and French border, in a way. My department has about 24 researchers and engineers. It's maybe interesting to know that most of them are longer than 10 years involved into the fuel cell science. So I would say it's a very, very experienced team which we have. As we are a Fraunhofer Institute, our mission is to work together with industry and to assist industry in developing their products. So we are at Fraunhofer, we are always measured in our earnings, which comes from industry, and we are quite happy that about 40% of our earnings are based directly from industry. Our core competences are shown here. So I would say we are relying on 4 pillars. So first of all, and what I'm going to talk about is our in situ characterization. So how behaves an fuel cell MEA within fuel cell operation. Second is the analytics, to look at the fuel cell MEA regarding the microstructure or element distribution, things like that. Third is the modeling. I would say to understand the physics and the electrochemistry of a fuel cell, and understanding in a scientific community always means that you are able to model the physics. So this is our third pillar, and the fourth pillar is production research, which means that we are able to produce our catalyst layers by our own, to manufacture state-of-the-art CCMs, and to really investigate the correlations between production processes, the microstructure which you get from different process operations in your manufacturing plants, and the behavior inside the fuel cell. I'm going to talk about the characterization, so the in situ behavior of this fuel cell MEA, which is the heart of the fuel cell. This is a view into our main characterization labs. We have several labs on top of this, but inside this lab we do the MEA characterization in terms or with means of a so-called zero gradient cell. I will show you later on. Some years ago we started to develop our own test stations, and this is how our test stations look like. They are fully automized, and not only the operation is fully automized, but also the characterization. We can apply, I would say, all advanced electrochemical measurements, which is of course polarization curves, impedance spectroscopy, cyclovoltammetry, limited current density measurements, but also CO stripping, or we are developing the measurement of CO displacement right now. So with this in situ characterization, we can look at the behavior, the performance of the fuel cell MEA. We also look at degradation effects. We can do estimations regarding the microstructure, so differentiate between diffusion in macropores or in micropores and so on. And this helps a lot to better understand why a fuel cell behaves the way it does with respect to different operation modes. Typically, we use this test cell, which we developed some years ago together with the company Baltic Fuel Cells. The booth of Baltic is over there, and we like this cell very much because it enables a very, very effective handling of the fuel cell, a simple exchange of the samples. What you see here is the flow field, so we get our MEAs from our customers, we put them into it, and then you can do, as the title of my talk is, a scientifically sound characterization of the fuel cell. It's a so-called zero gradient test cell, which means that we really can have a good control of the operation parameters. So we have a clearly defined temperature, clearly defined humidity, current density. So as the name says, it's zero gradient, so very well-defined operation mode of the component MEA, and of course this allows to draw reliable results out of the measurements. To show you some of our results, in this case we investigated the CCMs with different catalyst loadings as shown here. So different catalyst loadings here, and we manufactured the CCMs by ourselves. In this case, we used screen printing, and we printed 4 layers, up to 4 layers on top of each other, and this is why the height of the catalyst layer is differentiated from each other. So low loading means 1 screen print with a dry height of 3 micrometers, and then with the higher loadings we have 4 layers on top of each other printed, and that's why the height of the catalyst layer is different. And then we can, over time, with a certain aging profile, we can estimate the electrochemical surface area over time or over the cycle loads. And I wanted to show you our possibility to do the limited current density measurements, which allows you to differentiate between the so-called Knudsen diffusion, which is the oxidant diffusion in micropores and the diffusion in macropores. So we also can investigate the different behavior regarding to different catalyst layers, thicknesses, and different catalyst loadings. If you want to read more about the results, I always posted these links, which you can see after the talk, and you can download the talk, and then you follow this link, and you find a very comprehensive report about this. Another example is contamination effects measurements, which is shown here. So we applied into the hydrogen gas, we applied different H2S contaminations, and on different CCMs with different platinum loadings on the anode side. And then we can investigate how harmful this H2S is to the fuel cell. To go on, also, of course, the stability of the membrane is quite interesting, and we did investigations here with different membranes, different equivalent weights, and the addition of cerium, which is a scavenger for radicals. And over the time and the different, the operation time, we followed the fluorine release. So to estimate the, let's say the dissolution of the membrane. We don't stop with these zero gradient cells, which I have shown you so far. We also do a short stack characterization, and just to give you some impression regarding this. In this slide, I show some results regarding our free start investigations on the platform of the AutoStack Core project, which was a European project some time ago, where a larger consortium developed this platform of an automobile fuel cell stack. And you see here that we were able to realize these free start and had some very interesting free start results. Yeah, and I got already the sign to come to an end, which is now. So if you like to hear more, please ask your questions right now or come over to our booth C39 over there, this direction.
Thanks a lot for this great presentation. Any questions? You have the chance to ask one question, and if you find this question later, you have seen it, it's C39. Okay.
Thank you very much again. Bye.
Wolf Groos.
Yep.